So this is Yotta's paper 2 mock paper for TMUA, and we'll just get straight into it, I guess. Which of these statements is true? This one is because 19 squared is this. This is not true. We saw this actually in paper 1 as well. X squared rooted is actually the modulus of x, because of course minus 5 squared is 25, rooted is 5, and you're not back where you started. So yeah, that's not true. This isn't a polynomial because polynomials need integers up here. This is an integer. If you do a little bus stop, you'll find out, or if you just know your times table is up there. This is obviously not true. This is kind of nearly true. This is actually equal to ipi, amongst other things. There's more solutions as well. But anyway, 15, so D will be the answer here. Nice, easy warm-up question. N is prime if this or that for some integer k. Well, n is 35, we'll choose. And 35 is 6 times 6 minus 1. But 35 isn't prime, so that's not true. N is prime only if this or that. Well, 2 and 3 tend to break the other prime rules. Actually, this does work for anything that's not 2 or 3, but 2 or 3 are not in this form. So yeah, neither one of those things is true. Question 3 then. So yeah, this is the first question on this paper that I'm a little bit unsure about. Firstly, I happen to know all the primes end in these numbers, and that just cycles around. You just keep cycling. You know, this is 1 squared, and you get to 10 squared, and then these last digits just cycle around a bit. This is a square number. It's p times q cubed or squared. But of course, this number ends in a 7, which squares don't do. So this is not true. This one is true because it just so happens that you can write every single odd number ever as some thing squared minus another thing squared. This is the quick demonstration of that. You can keep doing that. You can also prove it. I'll leave it to you to prove that properly. But anyway, so I definitely know we can do this. Now, this one I was very unsure about. A bit of Googling told me this theorem here that said you can write a number as the sum of two squares if and only if its prime has no factor p to the k, where this prime is congruent to 3, mod 4, and k is odd. But this here, the digits here add up to 42. So this has a factor of 3 in it, which is, of course, congruent to 3 mod 4. But only 1 3 in it. It doesn't have a 9 because this isn't a multiple of 9. So therefore, this breaks this rule, and we can't do question 1. I'm sure Yotta will turn up in the comments and explain to me how I was supposed to do that without just knowing this theorem. I don't think TMUA could ask this question in real life because I don't think this is an expected piece of knowledge for anyone to realistically have. But anyway, question number 4. Function is defined for this. So f3 is this, f of 5 is that. So it's above and below the line. F of k has 3 solutions in this interval, so it could be some kind of thing that goes up, that goes down, up and down again. Or it has an odd number of solutions in there, so it could go a few times in between. K is necessary for j. So k was this one here. Is having 3 solutions necessary to do that? Well, no, right? Because you could have 1 solution and do it. There's that example there, so that's not there. K is sufficient for j. So is this sufficient for this? Well, no, because you could have 3 solutions but not go through this point 1 and this point minus 2, so it's not sufficient either to conclude it. And L is necessary for j. If you've got an odd number of solutions, is that necessary to have this? Well, he's never defined this as a continuous function. So what if the function, a very boring function here, what if it was literally just a flat line until like 4, and then a different flat line afterwards? That is a function, I think, and it doesn't have any it doesn't have an odd number of solutions between 3 and 5. So I think I'm going to go with none on this one, and I'll be good to go. Question 5. So if we expand this out, we get this. Now, this is very easy to draw, right? Except the domain of it is still restricted to be above 0 only, because if it was because you can't put anything less than 0 into here, despite the fact that you can into here, you need to consider the original way that they've given it. So this is the line at -9 gradient 1, but it doesn't exist over here. Now I've rearranged this to be in this form, so fairly straightforward. Of course, this would be a line 3x minus 20 is here somewhere. But of course, these x's do the same as these x's because of the mod. So it goes down and then up again. And looks like this, with this being -20 and this being -9. There is only one solution, just there, and it happens when x is positive, so we may as well just change that out for a proper x. And we'll just solve this for x is 5.5, and we'll have our answer. Question 6 then, so f dash to 5 is 0, and there's a turning point at x equals 5. So turning points do require the derivative to be 0. However, the derivative being 0 could form stuff that's not a turning point. For example, an inflection point. So therefore, P is necessary for this, but not sufficient because you don't know that it's actually a turning point there. Good, could be something else. So A, B, and C are 3 points on a regular n-sided polygon, with n being bigger or equal to 3. A, B, and C are on the circumference of a circle as well. So you've got a polygon. I've assumed that points mean vertices. Again, I'll be corrected in the comments if I'm not correct about that. But essentially, you've got some n-sided polygon going around here. A, B, and C are the vertices of it. Do I mean vertices? I do mean vertices, right? And you've got some number of sides between A and B, some other number of sides between B and C, and some other number of sides between A and C. So I've kind of started drawing it around like this. We're told about some angles here. I've gone back to primary school and I've done this in degrees instead, just because it makes what I'm about to do easier. So this is 150, this is 72, and then you do 360 minus, and you get this as the other one. Now, if you've got some number of sides in between A and B and C and C and A, then that means that we can say, well, how many degrees is kind of arcing around each side, is opening up to each side. So like we need to find a factor of these three things such that we can share that number across however many sides there are in between these two sections. Now the highest common factor between those three things is 6, which means, okay, we could just say that each side takes up 6 degrees, and then there'll be 25 sides here, there'll be 12 sides there, and there'll be 23 sides there, and those add up to 60. Now you could have said that these three things have a factor of 3 in them, and therefore you could divide all these angles by 3 instead to find the number of sides that are there, and you'd obviously just end up doubling each of these values. But that's not necessary. Like, it's necessary that it's a multiple of 60. It could be 120 if you choose to have 3 degrees per side either, but it's necessary that it's a multiple of 60 because this is the highest common factor there. Question number 8, find a counterexample if it exists to this. So the integral between 0 and 1 is the area enclosed by the x-axis. X equals 0 and x equals 1 and the function, which is exactly what you get taught in year 12, right? Except you then immediately get taught that sometimes that goes wrong. For example, if the function goes from being positive to being negative in that range between 0 and 1, then the integral will start cancelling things out. Or if the function is entirely negative, the integral will just give you a negative, which isn't, like, area isn't negative. You have to get rid of the negative at the end. So we're looking for a function here that either goes from positive to negative and therefore ends up with some cancelling, or just is in the negatives at all, because then you'd end up with a negative answer. Now this is clearly a positive function, so that's not going to help. By the way, it says if f of x is defined for this, well, that's not defined for that, so we'll ignore that straight away because it's not defined for 0 at log of x. Now this, if you expand out, is this, and that is just 1 minus sine squared, but the other way around. So that's minus cos squared. And cos squared lives above the x-axis, right? So minus cos squared lives below. So we found something we're looking for here, and I think B will not do this properly. Question number 9 then. So you can follow this through if you really want to. Everything works really well, all the way up to part number 4, where he's just cancelled a couple of integrals. Now, you can't just cancel integrals like this, because integrals are only equal up to the integration, the constant of integration. Right? So when you actually do this integral, you'll end up with the same thing as over here, except you'll have a plus c here, or a c1, and a plus c2 over here. And of course, those things will cancel, or will work together to solve this problem. Right? So if you're cancelling integrals like this, you can do that, but you need to put in a plus c. And then, of course, you just end up with c equals 1, and it would work fine. So the problem is on line 4. You can't just cancel integrals without dealing with a constant. This question here, then, so bring this 2 down to the front. This is obviously x to the minus 6 here, and you can put this minus 6 to the front. Now, I put this in because technically it's correct, but it's, I think, kind of unnecessary for this question, so we'll just ignore it. I didn't put this 2 down at the front because, I had a bone to pick here. I didn't like this notation. I sort of understand it, but I prefer to see some brackets around here. I'm only annoyed about that because I spent a couple of minutes bringing the 2 down to the front because I thought that's what it meant. I guess it's clear because the brackets are here and those are very different, but I'd prefer to see some brackets around the whole log. But anyway, regardless, so we've got a quadratic here is what I'm trying to say. This mod sign doesn't end up mattering. We're just going to ignore it. And we'll just do a quadratic thing. So we'll check for the discriminant. Obviously, we want 2 real solutions. So b squared minus 4ac greater than 0. And we'll do that. We'll get k is less than 9. Now, we do just want to check because, of course, I formed a quadratic out of log of x, and x can't be negative. So we do want to check, when you look at this solution here, can k be less than 0, or does the log somehow mess that up? Well, the way that I checked that was I just solved this equation using the quadratic formula, and I decided, what did I decide here? I decided that, oh, if you use k as -1, so yeah, if you use k as -1, I decided this is just fine, right? That this is just fine because this is a proper number, that's fine. 6 plus that is fine, 6 minus that might make negative, but then you just do log to a, or e to the power of a negative, and it's all fine, and you get two solutions for x. So I decided that was all okay, and the answer was just B. Question 11. So this thing is a number that only has ones in it, and it's divisible by 7 if and only if. Get out a bus stop and try stuff. Multiple of 3. Well, this doesn't work. 7's going to 1 0 times. Keep going. I'm sure you don't have to learn bus stops. It's not a multiple of 3 because you end up 7 into 41, which is not going to work. So let's go to the next one, multiple of 6, and we'll just put in some more stuff. So that's 5 times, is that? 7's 35, yeah, 6 left over. Keep going, keep going, keep going, keep going, and it ends up working. So that's good. So multiples of 6 work. Multiples of 7 clearly don't work because if you added another 1 in there, you'd end up with a remainder 1. So that clearly, or whatever it would be. So that clearly doesn't work. Multiples of 12 could work for sure. Why have I crossed those out? If and only if. Does that matter? Oh, if it was a multiple of 12, then it's a multiple of 6. So that's not only if. So yeah, that goes away. And this it doesn't work for k as 1, right? Because 4 times 1 is 4 plus 6 is 10. This clearly wouldn't work for 10 ones because you'd have 4 more ones. And we saw before that 4 ones ends up with a remainder at the end because we had to keep going. So that clearly doesn't work. And nor does this, because if you put in k as 0, you get 4, and 4 ones doesn't work, as we said. So multiple of 6 is the only thing that we can choose there, I believe. F of x is this. It's a cubic. For this, find the maximum f of x. I like this question. This could completely be in your TMUA paper. It's a classic kind of thing that they like asking. F dash of x is this. You set that to 0 to find some turning points. You find two turning points at 7 over 3 and 1, which are both in this range. So that's kind of interesting. So if we get out the picture, it's a negative cubic, right? So it's going up from here to down to there. Got solutions at 7 over 3 and at 1. Now, what have I done here? Have I already put those in? Oh, when x is 1, do we get 0? Have I magically figured that already? 5 minus 1 minus 7 plus 3? Yeah, that's 0, right? Yeah, sure. It seems like it would be 0. Cool. And then if you put in 7 over 3, now that's a minimum point, so it must do this, this, this. So if you put in 7 over 3 to this, I haven't actually bothered to calculate this. Notice that the graph goes through the y-axis of 3. Now the thing is, if this maximum point is bigger than 3, then that's the maximum in the range 0 to 4. But if it's less than 3, then 3 is the maximum. So the maximum isn't necessarily the maximum in this area. The maximum is a local maximum, but in the wider area of 0 to 4, it might be that this is bigger. So let's just look at this and decide, with as little calculation as possible, is that bigger than 3 or not? And just do some estimation. Just pretend these are 2's, maybe. 5 times 2 squared is 20. 2 cubed is 8, so that's 12, is it? Minus 14 plus 3 is slightly bigger than, is 1, isn't it? Or something like that. This is only slightly bigger than 2, but this is the one that gets biggest the fastest, is it not? Maybe? Or does this one get bigger faster because you're timesing by 5? It's probably this one, right? But then you're taking away this as well, and there's 7 of them, man. I just decided, maybe lazily, I might have got this wrong. I decided that 3 was bigger. I also decided that this is probably a trick question, and the whole point of the question is that 3 is bigger than this. So I think that's what was why I was super lazy. I'll type it into a calculator while this video is uploading and check that. But if I've got that wrong, then funny. Anyway, a word is good. In fact, what this actually is probably one of these, right? Or this. And those are all smaller than 3 except for this one. But it's not this. Those are, so yeah, I'm happy with that. A word is good if and only if it consists of these 4 letters. Examples there. 5-letter good words have at least one A and at least one C. So how many 5-letter good words are there? Well, that's just 4 to the 5 because you can choose any of these 4. And there's 5 of them. I'm going to get rid of everything that doesn't have an A in it. Now, if you're not getting an A, then you have 3 other letters to choose from. So let's take away 3 to the power 5. And now let's take away anything that doesn't have a C in it. Because again, you have 3 letters to choose from, so that's going to be take away 3 to the 5 again. Except here, I've taken away a couple of things more than once. So for example, the word D. I've taken away twice because it doesn't have an A in it and also doesn't have a C in it. So I'm going to add back in the words that don't have either an A or a C. And of course, there's 2 to the 5, lots of those, because they just have B's and D's in them. And I think this will work out as our answer. And I mean, this is 2 to the 2 to the 5, so that's 2 to the 10, so that's how I worked out of that. And then I just did this. And then I just used the last digit to work out that the answer must be this, because the only ones with zeros are these, but this looks like it's 570, so that's good. Question 14. Which of these is the smallest? So this is slightly bigger than 2, because 3 to the 2 is 9, and e log to base e, obviously e is less than 3, so this is bigger than 2. 3 to the power log 3, 2 is 2, because this cancels. And this is bigger than 3, so therefore base being bigger makes this bigger, so that's bigger than 2 as well. 668 times 2 is this, so this is slightly bigger than 2 as well. I'm essentially just hoping for something that's less than 2, because I don't want to have to compare any of these. Now, cos of pi is minus 1. Now, 3.14 is ever so slightly less than pi. So you go back on the cos graph ever so slightly, which means you're just less than when I say just less than minus 1, you're like minus 0.999, right? Just above minus 1 on the number line there. So when you times that by 2, you get like something ever so slightly less than 2. So okay, this is a candidate, except this is much less than 2. I know this is because 2 cubed is 8, so this is much less than 2. So this and this is I reckon this is like basically 2. So this is definitely a candidate so far to win. Now, sine is repetitive every 4 pi, so this is the same as sine of pi over 6. Sine of pi over 6 itself is, let me get this right, is a half, is it not? So 3 to the power half. Okay, so that's the square root of 3. Now, how do we compare, I haven't done that twice. Okay, how do we compare root 3 and cube root 5? Well, what you do when you're comparing roots is you just square and cube them out until you get like integer numbers, because whatever squares to a big number was bigger itself, aside from minuses, but there are no minuses in here anyway. So that's not just cube these or square these, because one's a square root and one's a cube root. Let's just raise both to the power 6, because that way we'll get 5 or 6 over 3 is 2, 5 to 2 is the 25. Raise that to the 6 is 3 to the 3, which is 27. Because this one to the power 6 is less, this is the smaller number, and we'll have our answer of E. Question 15. Which of these is true about P and Q where P is prime? Not sure about Q. The highest common factor is 1 if Q is also prime. Well, if Q was the same prime, like 7 and 7, the highest common factor is 7. So that's not true. PQ has 4 factors. Well, if Q was... let me figure out why I've underlined this. If Q was... Oh, well, surely if Q was just some random number like 16, and P was 7, 7 times 16 has way more than 4 factors. So, yeah, sure. Good. 16. That's fine, right? Yeah, that looks fine. Of the following 7 statements, which is correct, if only one of them is? The way to do these questions is just to pretend the top one is true and work your way down. When you end up with a contradiction, you pretend the second one is true instead, work your way down, and so on. So let's pretend the top one is true. If n is even, so this is lamp 1, lamp 2, lamp 3, lamp 4, we'll just pretend there are 4 lamps because we may as well. If n is even, lamp n is switched on. So that means 2 is on and 4 is on. So that's true now. We now need to make all of these false. If n is odd, lamp n is switched off. So, and I want that to be false, so I need at least one of these to be on. So let's do on and off. I want this to be false. If n is even, lamp n is switched off. Well, that's clearly false because it directly contradicts that. If n is odd, lamp n is switched on. Well, you can see what I've done here. I made this one. I didn't just turn them both on. I made one off, one on to make this one also false. So that's good. If lamp n is switched on, then n is even. Well, that's false because 1 is on and 1's not. Lamp 1 is odd, but it is on. If lamp n is switched off, then n is odd. Well, that's actually true. And there doesn't seem to be much I can do about that. So let's cross out option A and go to option B instead. If n is odd, lamp n is switched off. So let's go the other way around. We'll do exactly the same thing. We'll make one of these on, one of them off. That will make all 4 of these correct. N is switched on, then n is even. Well, that's actually correct. N is switched off, then n is odd, not correct because of this one. So it's the same situation as before. C then, if n is even, lamp n is off. So we'll turn both those off. Let's make all the others untrue, again by going on, off on the odd ones. So we're focusing on this one now. Lamp n is switched on, n is even. Well, that's fine. Sorry, that's false, isn't it? Which is good. I want it to be false. because the only one that's on is this odd one. N is switched off, then N is odd. That's false because of this one being off and this one being off. N is switched off, then N is even, is false because of these two as well. So yeah, good. Question number 3 doesn't seem to have any contradictions if you set up a bit like this. Question 17 then, how many of these functions is f dashed of x increasing? So we have to work out f dashed of x for all of these, and then derive again to find which ones are increasing functions, because the function we're talking about is f dashed of x. Let's find f dashed of x for all of them. I mean, they're not hard to find f dashed of. And we want these functions to be strictly increasing, so we want the derivatives of these to be positive. Except we can just think about the graphs in our heads. Like, this is clearly not strictly increasing because cos goes up and down all the time. So that's fine. This is strictly increasing, right? Because it's just 2x is just a number. So that's at least one of them. And I've underlined one already, so apparently the others aren't. This goes up and down because it's a quadratic, so that's not strictly increasing. This one here goes, what does it do? It's in these two quadrants, isn't it, with C shapes. But they're not strictly increasing because, why isn't it strictly increasing? Oh, because it's negative? No, that doesn't make sense. What have I got wrong here? That feels in my head to be an increasing graph. Is it because, oh, for all real x, of course. This doesn't exist for certain x's. So, yeah, goodbye. Doesn't work. And likewise this one. So actually only this one works. This is maybe you would say an increasing function, colloquially, or if you weren't being too careful, but it doesn't exist at x equals 0, so it's not increasing for all x because it doesn't exist for all x, and we're good to go. All permutations of the word number are made alphabetical. In what position is number? So, okay, these are, and this is what took me the longest in this question, these are the letters of the word number in alphabetical order. So we want to start with an N, so we need to get through all 3 of these first out the way. So what we'll do is we'll say, okay, when you pick B, E, or M to start, there are 5 factorial permutations of the rest of the word, and we want to get through all the B's, or these, or the M's at the front. So that's 3 lots of 5 factorial to get through before you reach your first N, then some other stuff. That's, by the way, 360, because this is 120 times 3. Now, once you've arrived at N, your next thing to do will be you want to get the letter U next. But once you've got N first, you need to get through all of the second letter B, E, M, and R's. So that's going to be 4 lots of 4 factorial to get through, because there's going to be 4 other things in the word to arrange. If you're trying out, say, N and then E, there's going to be 4 other things to rearrange. But you've also got the 4 that you could put in the second letter before you get to U, which are these 4 here. And this is equal to that. And then we'll be at NU. But once you're at NU, this is the alphabetical order, and we don't want that. We want M to come next. So we need to get through these B's and these. So there'll be 2 things to get through, each with 3 factorial arrangements in them. So that's 2 times 3 factorial. And then you finally get NUM. But then actually, NUM, once you've got the M here, notice how it just makes the word number. So will be the next one. So we do this plus this plus this, and then will be the next one, which will be 469, I believe, and we'll have our answer. Okay, a square free integer is a positive integer which isn't divisible by a square. So that means when it writes as prime factorization, there's no repeated prime, right? Because the moment you have a p squared, well, then it's divisible by the square of a prime. So its prime factorization is just a load of different primes appearing a single number of times. For example, this number here, or this number here. So which of these statements is correct? Square free integer is with n prime factors has 2 to the n factors. Now, this is something that I think I've made a video on in the past, but the number of factors that a number has is you take its prime factorization, look at all the powers in it, add 1 to them all, and then times them all together. So as I said, a square free integer has lots of powers of 1. We add 1 to all of those to get lots of 2's, and then we multiply all those 2's together. And if there are n primes, then that will be 2 to the n factors, because there will be n 2's multiplied together. So 1 is correct, I think. I think that's completely fine. The product of 2 square free integers is always square free. Well, these 2 examples disprove that, because you end up with a square when you multiply these 2 things together, so that's completely wrong. And a square free integer cannot be a power of 36. Is 1 square free? Or is, sorry, 1 is a power of 36. And is 1 1 also isn't divisible by square of a prime. So is that my counterexample? Nice, that was smart. I hope that works. Anyway, question 20. Um, question 20. So this took some time. I mean, this, as soon as I read this felt like such a bait, like the fact that it's telling you directly to do this. So I was trying to look for tricks. I couldn't find any. It went into Warfare Alpha, which told me the answer. I then had to try and work out what it was trying to do. Um, okay, here's what I think is the best way of doing this. You take this equation down here, this last one, and you times it by minus a fifth to make this. You then do this equation plus this equation plus this equation. And the way that I'm going to write that is I'm going to put the x's first, then the y's, then the z's, then the numbers over there. So that's just the 3 equations added together. But now what I'll do is I'm going to complete the square on the x's, the y's, and the z's separately on their own. The y's are a little bit more tricky because you've got 3 here, but it shouldn't be too hard. There shouldn't be a squared here. That's just a complete mistype. Sorry, so bring the 3 out, so you just get left with this. And then you complete the square here, which looks like this. Then you multiply the 3 out again. I'm collecting some numbers vaguely around the outside as well. And you end up with all this, which you collect together. And I think you end up with this here. But of course, this is a square number, which is greater or equal to 0, plus another number greater or equal to 0, plus another number greater or equal to 0, apparently equaling minus 2. So this has no solutions, and this was a complete bait. There are no real solutions of this, so you can't find this. So therefore, no solution exists. It was actually ended up being quite a nice question, although it more of my life than I'd like was spent on that. Thank you for watching, and thank you again to Yotta for writing that.